PowerPoint, so you probably didn't need that, but I'm used to projecting. So anyway, thank you. It's very useful to have that talk before me because it explains a lot about the way that the sampling and such like does. Because those of you who know me, I'm an archaeologist. I'm not an AI person. And this project sort of came about quite a lot by serendipity and a sort of chance meeting. So we think it's proven interesting and hopefully useful. So I'll begin by giving a brief overview of how the data was originally acquired, and then follow on by the steps that led to the project. Said in the abstract that I hope to have some answers. I've got some answers about the project, but none about the data. So brief introduction to those of you who don't know Historic England, since I'm the first person here speaking. We are the national body tasked with the protection of the historic environment in England, which includes the designation of nationally important sites, but also research regarding all the other sites. So, background to the project. We have been, within Historic England and its predecessor organisations, mapping the archaeological landscapes of England for over 40 years, and we've mapped about 50% of the country. And this is just a map showing the areas that we've covered. It's worth noting that all this data is freely available to view through a simple web-based application, but also to download through the Data Hub. So anybody who wants to use this data for research purposes can do so. However, not all of the data is equally accessible. If you look at this is the complete coverage. This is what is available in digital format with attached data such as period, type, etc. And as you can see, there are very large areas, early projects, where we carried out mapping physically. We drew inked overlays on permatrace, and we created a monument record at the same time, recording this information, but there is nothing attached to the data. So one of the things that we wanted to do for a long time is to... Okay. Yes. So you can see this data is also available through the Mapping Explorer, but it's only available as a mosaic raster layer without any attached monument data. As you can see, some of it is very important archaeological areas, such as here in the Thames Valley, where you've got an extensive prehistoric landscape. We've attempted to attach some data to this by linking it to pre-existing monument records, either held by Historic England itself or by local and regional historic environment records. But as you can see, there are bits missing. So, after doing some manual testing in 2022, we decided there had to be a better way of doing this. And so we put out to tender and contracted an external geospatial analysis company from India with a remit to create monument polygons from all of this raster data and attach the most relevant attributes to it. Now, this is different from what pretty much everybody else has done, because they've been looking for new features, they've been analysing LiDAR data. We've actually got this data which has been mapped by archaeologists, and we're pretty clear that we know what it is. We just want to be, we wanted a better way of analysing it and quality controlling it. So because they were non-archaeologists, there was a sort of an element of training about it. Here you can see, is that the pointer? So which is the pointer? Ah, there we go. Here you can see a small enclosure, and there was the monument record, and they came up with that. Here, there's a series of different enclosures, and they came up. So in general, it was a very positive project. And they provided Historic England with about 50 56,000 monument records. But there were some issues, particularly due to the fact that a lot of the records, as with that first example of a point, only exist as points or very small sort of generic polygons that have the monument data. And sometimes these didn't quite match, and therefore they didn't record the correct information. Here you can see that little diamond is the monument record for this area of historic mining. And because it didn't quite match the area, they didn't get it right. Here, the record for 32276 is a small find of a Neolithic axe. But anybody who knows anything about archaeology would expect that that's probably a Civil War fort, not a Neolithic axe. And the same here. The find, which is closest to this area of crop marks, is actually that. And so this was classified as a small find of flint scrapers. Obviously, it should be linked to this, which is a generic record for a large area of crop mark sites. So, what to do? This is where serendipity comes in. Through another project that we're working on with Andy Bevan at UCL in London, we were introduced to Bjorn Menzies at the University of Zurich. Now, Bjorn is a computer scientist in the Department of Quantitative Biomedicine who specializes in biomedical image analysis and machine learning, which doesn't really sound like it's going to help us, but he thought that the techniques which he used could be applied, and hence this project. One of the things is, as the previous talk said, you need a lot of sample data, and we have got masses of sample data because we've been mapping the country for years. Because we wanted to use this data to analyze the raster data, we realized that the first thing we had to do was a proof of concept on the digital data. So we focused on that. And here you can say, when we say we've got a lot of sites, we've got 107 project areas, we've got literally tens of thousands of records, each of which has a physical depiction on the map, as well as a monument record that records, as I say, period and type, etc. So he looked at a small area in the southwest. Here you can see it's about 10 kilometres by 10 kilometres. And what you can see on here is that the blue outlines are the monument records which have the period type interpretation, and the green is the actual detailed mapping of what was seen. So as I say, each of these has a record. You probably can't read it, but that says period, medieval, type, ridge and furrow. And here is the relevant image patch that goes with it, as he records it, the binary outlines. Again, it was interesting from the previous talk that one of the great advantages of this project is because you are using mapped data, you haven't got any of that background faff. You've just got a single image, you've got a single black and white, or in this case, green, whatever, image to deal with. So a separate example here of a Bronze Age round barrow. So the idea of this study, which is where I have to now start looking at my notes more because this is the AI side, is to use a convolutional neural network, easy for you to say, image classification algorithm to produce type and period labels based on the spatial map of recorded archaeological features on the ground. I've just realised I read that off the slide, which you should never do. But basically, it addresses the technical questions, looks at how we might be able to improve this and all the limitations. So the basic prediction task, image classification, as a previous talk spoke about. You've got an image patch, the algorithm runs through all these differences and predicts your class labels. That's the theory. This is a nice little image to show it in simple terms. You put a photo of a cat in, it runs through lots of other images, and it comes out, yes, this is a cat. the technical bit. ResNet 34 is a widely used, easily available and proven model for this sort of image classification. There are various elements that have been built into the program, such as class weighting and data augmentation. And the five-fold cross-validation, I am told, is you split your sample into 10 blocks, into 5 blocks, you train it on 4, and then test it on the remaining. It's going to be fast, right? The problem is that we don't just have one label. We're looking at a period and a type, and each of the periods is different, and each of the types is different. So, going back to the cat-dog analogy, we don't just want a cat. We want to know, is it Siamese? Is it Burmese? Is it long-haired? Is it no-haired? Is it white? Is it a tabby? That's just the type. Period equates to age. Is it young? Is it old? Is there more than one? Is there actually a dog in there? Does it even look like a dog? So you've got an awful lot of questions that need to come out of this data. And that's before you even start talking about the issues of image patches. Because of the size of the features ranges from 1 meter to 10 kilometers, what size image patch do you use? I've got more detail on this, but I'm now running out of time, so I'll go through. You've also got the variety of images, of data in an image patch. There wasn't the possibility to actually go through masking, so they were looking at each, what turned out to be half a kilometre square area at the same scale. So you've got examples where you've got 2 lots of images in the same thing, the cat dog. You know, you've got a Bronze Age settlement next to a medieval ridge and furrow. Labels. I've talked about that, so I'll move on to the next one. Data imbalance is a big one because you know that there are certain types of features that you find a lot more regularly than others. Medieval ridge and furrow is going to massively outweigh almost anything else. Likewise, Bronze Age barrows. And again, predicting mixed labels. The initial analyses also looked at the hierarchy. Because the training system has labels which have a hierarchy, i.e. if it's early Bronze Age, it's also Bronze Age, it's also late prehistoric, it's also prehistoric. If you analyse for prehistoric, it's very good. It gets like 60%. You analyse for early Bronze Age, it gets 20%. So, next steps. There's been a lot of complexity. One of the things that we're thinking about is running a sort of triage. So using, looking for those very simple features like medieval ridge and furrow, Bronze Age round barrows, run the program once and extract all of those. Then when you run it the second time, you don't have the same imbalance. You've got a more regular level of the numbers of features. Should we actually consider revising the training data? We've got a lot of very specific data in there, particularly from the Second World War. We've got a type 24P-F3 pillbox. Does it really need that? Can it just be a pillbox? Mixed patches. That's... For the training data, it's fine. Somebody else can decide what type of pillbox it is. And then there's a question of additional data sets. You know, would it actually be useful to have the general DEM elevation model to work out the elevation of the land, etc.? And then only once it's been proven on the vector data can we apply the rasters. The question is, how big an issue is it? And this is where I've just realised I haven't got the most up-to-date version. The sample area, at the same time as we were running this project, we also had people manually checking all the data that DSM came back with. And we looked at an area in central England of probably about 40... Sally, any idea? No. Okay, it was quite a large area and it came up with 1,200, approximately 1,200 sites. And it was assessed in a relatively short time. The point is that of those 1,200, 1,500 odd sites, almost 1,400 were correct. A small number were needed to have the polygon amended. One was completely deleted because it lay within a polygon that already existed, and 23 had the incorrect ID. So, in summary, it's clear that image classification does offer us an avenue for classifying recordings of archaeological features, but I think it's got a long way to go. The information on the site features can be easily amended by additional information, and the class hierarchies almost certainly require revision to better group the features and remove some of the more extraneous ones. The other factor, which I didn't mention, is that performance is limited. As I say, we settled on a 512 by 512 meter image patch, which comes in at 2 meter resolution. Now, those of you who are used to using LiDAR know that 2 meter resolution isn't great. Because you're actually working with map data, it's probably less of an issue than it would be if you were trying to extract it from a LiDAR or something like that. But that's something we could look at. I said, why can't you look at 1,000 pixels by 1,000 pixels? And the answer is that the CNN simply can't cope with it and your graphics card falls over. But the bottom line, which came out of the final thing, is it actually going to be quicker than doing it manually? So my acknowledgements first, foremost, and almost entirely to Bjorn, because I couldn't have done any of this. He has led the technical side of the project. So if you've got technical questions, sorry, he's not here. And thank you to all the staff at Historic England and the various contractors who have created the mapping, because we wouldn't have had anything to do without that. So thank you.